Every time a mantis shrimp throws a punch, it creates a tiny bubble in the water behind its claw. That bubble collapses in nanoseconds, reaching temperatures that rival the surface of the sun, and releases a flash of visible light in the darkness of the ocean. The strike itself accelerates with the same profile as a .22 caliber round. And if the claw misses, the shockwave from the collapsing bubble still hits hard enough to crack shell. This animal is 6 inches long, and its fist breaks the laws of physics every time it eats lunch. So how does an animal smaller than your hand generate a strike that would impress a ballistics engineer? It starts with a problem that evolution had to solve. Muscles are slow. Even fast muscles, kind that let a housefly dodge your hand, top out at a certain contraction speed. For a predator that hunts armored prey on the seafloor, snails and Blake's side, calcium fortresses, muscle speed alone will never crack the safe. The mantis shrimp needed something faster than any muscle fiber could deliver, and it had to work underwater, in a medium that fights back against rapid movement with 800 times more resistance than air. There are over 500 species of mantis shrimp, and they split into two broad weapon categories. Spearers have barbed appendages designed to impale soft-bodied prey like fish. Smashers have rounded clubs built to obliterate hard shells. The physics we are talking about belongs to the smashers, and their weapon is one of the most refined striking mechanisms in the animal kingdom. The solution is a mechanism that engineers would recognize immediately. It is a spring-and-latch system, the same basic principle behind a crossbow. The mantis shrimp contracts large extensor muscles in the upper part of its arm, called the meris, but the arm does not move. Two tiny structures called sclerites brace against the interior of the meris and lock the system in place. Energy builds. The muscles keep loading force into a saddle-shaped piece of exoskeleton made from chitin, compressing it like a drawn bow. When the latch releases, all that stored elastic energy converts to motion in under 3 milliseconds. The entire strike is over before a human eye could register it started. According to Harvard Seas researchers who built a robotic model of this mechanism in 2021, the acceleration profile mirrors that of a .22 caliber bullet leaving the barrel. Their robot, modeled on the mantis shrimp's 4-bar linkage system, reached 26 meters per second in air. The living animal achieves comparable speeds underwater, punching through a medium that should make those velocities close to impossible for something without an engine. But the punch itself is only half of what makes this weapon so dangerous. The other half is something that happens after the claw connects, or even if it misses entirely. When the club tears through water at that velocity, the pressure immediately behind it drops below the vapor point of the surrounding liquid. A small pocket of water vapor forms in the wake of the strike. Physicists call this cavitation. The bubble exists for only microseconds before the surrounding water rushes back in and crushes it. That collapse is violent. According to research compiled at the University of Sheffield, the temperatures inside the collapsing bubble spike to roughly 4,700 degrees Celsius, approaching the surface temperature of the sun, and for a fraction of a trillionth of a second, the collapse produces a tiny flash of visible light, a phenomenon called sonoluminescence. The mantis shrimp is generating light from the force of its own punch. Not reflected light, not bioluminescence, light born from the physics of a collapsing vacuum. So every single strike is a two-part weapon. First, the physical impact of the club. Then, microseconds later, the shockwave from the collapsing cavitation bubble delivers a second blow. Prey animals get hit twice from a single punch. Even when the claw misses the target entirely, the cavitation shockwave alone can stun or kill small organisms nearby. Aquarium keepers have reported mantis shrimp cracking the glass walls of their tanks from the inside, not from direct impact, but from the cavitation shockwaves generated during feeding. You would think an animal punching this hard would shatter its own fist. A human boxer who hit a concrete wall at these accelerations would be looking at a handful of bone fragments. The mantis shrimp punches thousands of times between molts, and its club barely chips. The answer is in the architecture. Research published in Matter found that the club is built in 3 distinct layers, each solving a different problem. The outermost impact region is packed with hydroxyapatite crystals arranged in a helical pattern that disperses incoming force across the surface, rather than letting it concentrate at a single point. Below that sits the periodic region, where chitin fibers are stacked in a boulagon structure. Each layer of fibers is rotated roughly 5 degrees from the one beneath it, creating a twisted plywood effect. When a crack tries to travel straight through the material, it gets redirected, twisted, and forced to take longer and longer paths until it runs out of energy. The innermost layer runs parallel fibers that absorb whatever residual stress makes it through. This 3-layer design means cracks cannot propagate through the club. They start, they twist, and they die. The club absorbs the same forces that destroy the prey it hits. Material scientists have tested composites inspired by this architecture. According to research published by Purdue University, biomimetic materials modeled on the Boulagon structure proved about 20% stronger than identical materials without the helical layering. Engineers are studying these patterns for body armor, aerospace shielding, and impact-resistant vehicle panels. A 6-inch crustacean built better impact armor than anything humans designed until we started copying the crustacean. If you're enjoying this, hit subscribe. We cover creatures like this every week. The punch and the armor are extreme enough on their own. But the mantis shrimp also has the most complex visual system ever documented in any animal, and it works nothing like you would expect. Mantis shrimp have 16 types of photoreceptor cells. Humans have 3. That comparison led to decades of assumptions that mantis shrimp must see an impossibly rich spectrum of color, millions of shades beyond human perception. According to a 2014 study published in Science by researchers at the University of Queensland, that assumption was wrong. When tested on their ability to distinguish between similar colors, mantis shrimp performed poorly. They could not reliably tell apart shades that were fewer than about 25 nanometers apart on the visible spectrum. Humans can discriminate differences as small as 1 to 2 nanometers. So why carry 16 photoreceptor types if you are worse at the job than an animal with 3? The answer, according to the Queensland team, is that mantis shrimp are not comparing colors at all. Their visual system works more like a barcode scanner than a color mixer. Each photoreceptor type responds to a narrow spectral band, and the brain reads the overall pattern as a signature. Instead of blending signals the way human brains do to perceive a smooth gradient of color, the mantis shrimp brain bins incoming light into discrete categories. That's prey, that's a rival, that's a mate. The system sacrifices fine discrimination for speed. And for an animal that lives in a world of ambush predators and fast-moving territorial fights, speed matters more than nuance. In a habitat full of camouflaged prey and territorial rivals, signaling through color patterns on a coral reef, being able to categorize objects in a fraction of a second is a better survival tool than being able to appreciate the subtle difference between teal and turquoise. And then there is the polarized light. Polarized light is invisible to nearly every animal on Earth. Some insects can detect linear polarization, which helps them navigate by skylight. According to a 2016 study published in Nature Communications, mantis shrimp are the only animals known to detect circularly polarized light, where the electric field of the light wave rotates as it travels. Their ultraviolet-sensitive photoreceptors contain structures that act as quarter-wave plates, converting circularly polarized light into linearly polarized light that the underlying receptor cells can then analyze. The researchers found that mantis shrimp actively rotate their eyes, adjusting in real time to align specific photoreceptors with the angle of incoming polarization. No engineered optical sensor matched this capability when the research was published. Mantis shrimp were detecting a property of light that most physics students do not encounter until a university optics course, and they were doing it while hunting on a coral reef. The mantis shrimp uses circularly polarized light for communication. Certain body parts reflect circularly polarized signals that other mantis shrimp can read, but most predators and prey cannot detect. It is a private channel, invisible to almost everything else in the ocean. 2 mantis shrimp can signal each other in a frequency band that their predators do not even know exists. So you have an animal that punches with the acceleration of a bullet, generates temperatures approaching the surface of the sun through cavitation physics, sees in a dimension of light that no other animal can perceive, and wraps all of this inside an impact-resistant exoskeleton that material scientists are actively trying to reverse engineer. It does all of this at 6 inches long, living in shallow burrows on tropical reefs, eating snails. The mantis shrimp did not evolve to be impressive. It evolved to crack shells and avoid getting eaten. The fact that solving those 2 problems required a spring-loaded weapon, a double-strike cavitation system, a private polarized communication channel, and armor that outperforms engineered composites says something about what happens when natural selection has 400 million years to optimize a very simple job. If you like this, there are more stories like this on the channel.